All right, so this is just a continuation of where we were. This is actually week 2, day 1. Although I'll probably list this one as within the week 1. So if you guys are watching, kind of keeping up, if you miss a day or whatever, I'll put this one, the first part of today, in the week 1 section. I'm trying to categorize them. I haven't decided exactly how I'm doing it yet, but I haven't titled. I think we have 17 parts from last week, so just to give you guys a heads up. So it's kind of crazy, isn't it? We've done that much. So one of the things too is as we continue, these first 2 weeks we're not in the shop, so we have a lot more theory we do, and once we get to week 3, you'll see there won't be as many for those weeks as week 1 and 2. But anyway, just a heads up there. We finished our voltage ohm amperage discussion, I believe, and what I wanted to cover with you guys today is a few other variables, mainly with the alternator, and not charging system tests that you guys learned in basic electrical, but where we can have issues with AC voltages going into a DC system, in particular with the engine management system or anything that's computer controlled on the car. So let's start with this one real quick. And this one was kind of crazy. The picture really doesn't show the struggle that I had with this vehicle. It was a what? It was a Ford. It was a Contour. And okay, cool. I'm just trying to get my bearings here. At the bottom of this, I have a DTC. So I have a diagnostic trouble code for a P0320 as a crankshaft position sensor fault. Camshaft is P0340. Again, you'll get to know these codes over time. The P0s are our global codes. They mean the same thing on every car. That's how I know a P0320 is a crank code. So I'm looking at this Ford. It has no spark. I probably started with scan data, and of course the battery's dead. You get vehicles at these garages I work for that they've cranked the crap out of it before I got there, and of course the battery's dead, and that's the way it goes. So I have this guy's battery charger on this car on a lower charge, maybe 20 or 40 amp, and it wouldn't even crank, so I cranked it up to a 200 amp, and that was where I was when I was initially testing this thing. Connect the scan tool to the computer, of course with a stone dead battery. Any fault code that's in memory, as soon as I power it back up, I would look at that code as a hard fault, meaning happening right now. There's a term you guys need to learn. Let's write this down. A hard fault, because I use this a lot. A hard fault or a hard code equals a current code. Means it is happening right now. Okay? And then a soft fault or soft code would be it's an intermittent problem that is not happening right now. So get used to those terms. I say that a lot. Hard fault, soft fault, or hard code, soft code. Everybody understand what I'm talking about now? It's happening right now. Which one do you think is easier to work with? Absolutely, the current fault that's happening right now. One of the hardest things that we encounter in this field is intermittent problems. If you cannot duplicate it, you're not going to be able to fix it. This is where experience is going to be key in dealing with intermittence, because you've seen this problem before on other systems, or maybe the same system, and then you know where you're going. You at least have some direction. If you don't have experience with a particular car and you have an intermittent fault, good luck. You have no direction. So hard fault. I have some pretty good direction with this Contour, wouldn't you say? It's happening right now. I have a crankshaft position sensor code. So I immediately go after the crank sensor issue. I crank the engine, probably check for spark or fuel. I don't remember which one I did first. With a crank code, we're not going to have either. And I didn't. No spark, no injection pulse on this Ford. Check the crankshaft position sensor, and man, what did I do? I don't remember the full direction. It's been a while since I've done this. But ultimately, what we're looking at was what I saw. Let's see, this is a Ford, so Fords use, okay, that would make sense why I didn't see it. Fords use crank sensors that produce AC sine waves. It's a 2-wire sensor. We'll talk more about this in section 21, I believe, ignition system inputs. Some of the manufacturers would use a crank sensor that would look like that. It's called a Hall effect. And Ford, on this particular contour, did not. It used an AC sine wave. So I had, if I remember, a good sine wave on the crank. And then I think I checked the cam. And that's right. It was going toward a computer problem. Why? Because I had everything I needed. Cam and crank were good. Why isn't the computer doing anything or controlling these coils with this cam crank signal? And I think I started checking powers and grounds next, and I don't remember if it was the reference circuit that I caught this problem or not, but this was what I saw on one of the computer power feeds, was that picture you're looking at on the screen. I saw that and I'm like, what am I looking at here? That shouldn't be going on a computer power feed, right? One of the main feeds coming into the computer. So after seeing that, realizing, well, this battery is totally shorted, I knew that, and I had the charger on a high amp charging mode. Guys, as soon as I took this battery charger off and went back in the shop and asked him for a jump pack, the vehicle started right up. So I want you to understand that I was chasing a no-start condition that was never a no-start problem. This vehicle was a no-crank problem from a dead battery, shorted cell in the battery, and this guy was doing the same thing. He was putting his battery charger on it, cranking the engine over. The car wouldn't start. Calls me up, hey, come look at this thing. Guys, all it was a battery. So what are we looking at here? If you've ever seen battery voltage, say on a scope, you probably haven't. If you've seen battery voltage on a scope, when you're in this high amp mode and that battery is completely dead or shorted, this is what you can end up with. What are we doing? That battery charger, we're plugging it into a wall that's AC voltage, it's converting it to DC, and then we're charging the battery with it. And the battery is kind of an electrical cushion, if you want to call it that. And without that cushion of the battery absorbing these highs and lows, this is what was flowing through that whole system. DC computer systems cannot operate off of this. You got lows of under 6 volts and up to 12 volts. That's a pretty huge range. If you were to put a digital voltmeter on this, we just learned about the average reading of a meter, right? What would you see? Somewhere in the middle of this, we'd see that voltage level. 9 volts. That might raise a red flag maybe there saying, hey, I better put a battery in this before we go any further. You guys understand this variable? It can happen. All it needed was a battery. I almost put a computer in it. So a little bit of lesson on AC voltage here. This is a lead into our alternator problems too. I had another one, it's not listed here, but it was a Ford Taurus, and it was at one of my other garages, and it had a anti-theft fault code, and it was intermittent. So intermittently this car wouldn't start, and it was losing injection pulse, and I had trouble recreating it. You know, and they had already done a new ignition lock and key because of the code, but it keeps setting this anti-theft code. I was able to duplicate it by the second crank. So what I realized in testing the car, here's what I realized. I had the key on, I was doing some voltage checks, and the car died on me within 10 minutes of having the key on. I'm like, well, that's not right. That shouldn't happen. And so I started thinking about low voltage, weak battery, and to recreate that problem, because the customer said it was only in the morning, it would happen sometimes, and to recreate that problem, what I did is I put it in a clear flood. After I charged the battery back up for a little bit, I put it in a clear flood mode so I could crank it longer than normal. And then I let off, and then I let my foot off the gas. On the second crank, I intended for it to start, and it had a slow crank, and I was able to duplicate this anti-theft problem during the slow crank. Ultimately, what the problem was low battery voltage. And low battery voltage tripped that anti-theft computer into saying we had a theft problem and then it cut injection pulse. I was able to see it happen from low battery voltage. So lesson here is what? You're running into something that's crazy, right? Or you're running in really any no start problem or intermittent no start problem. If that battery is weak, do you think maybe we should replace it before we go any further? I think that would be the lesson here. If I didn't have a jump pack that day, I would have had a hard time justifying this picture without seeing the way this car would react to a steady DC volt that the jump pack provided me. So just put it in the back of your mind, another variable, low system voltage, can do some crazy things, a battery with a shorted cell, and you put a battery charger in boost mode on that, that may be your no start right there. So no spark, no injection pulse during crank with a crank code, and yeah, bad battery. Next one. This is a alternator issue, and I think, well, we'll talk about this one first. This was at a transmission shop, and I'm using my old school Snap-on Vantage. This is the MT2400. That's what I took this picture from. And this would be what we call a graphed, this is a graphed AC voltage signal. So this is not, I'm not looking at the scope, I'm not looking at, say, an AC sine wave and showing you that sine wave. What I'm doing with this scale is I'm taking the sine wave, which measures peak-to-peak voltage, and then gives you an average of that. When you use your digital voltmeters in the AC mode, that's what that meter is doing, is it's taking an average of this peak-to-peak AC voltage. I don't remember the formula for AC average, but I think it's peak-to-peak times 0.637 or something like that, and then that's the number you see on your digital multimeter. Okay? If you did a little bit more thinking about this signal, it's high the same amount of time that it's low. Where's your midpoint is 0, so you can't average it like that, and I think that's how it's done, is times 0.637. Anyway, what you're looking at to the left is not a scope waveform, it is a graphed voltage. When you graph voltage on the back of an alternator, and we want to go to the alternator, when you graph this, you want to be less than, this is at least what all the Snap-on equipment we have says, and it's the number I've been using. I'm comfortable with it. I used to use under 500 millivolts, and I think it's less than 300 millivolts, AC is allowable in that system, and that would be an average, guys, an average graphed AC, not the peak to peak. So not this 300 millivolt AC, and this is our average number. I'm going to show you another case study where we can emphasize this a little bit more. All right, but here's the symptoms with this vehicle. Transmission would go into limp mode. And when it would do it, the vehicle would violently shake, like to a point where, you know, if you had false teeth, it'd shake the false teeth out of your mouth. That was how bad this vehicle would shake while I was driving it. I don't remember why I suspected the alternator right away. I believe whenever it would act up, the gauges would go all over the place on the dash. And what I did initially, before I did this measurement, I just disconnected the alternator. And so I get this question a lot, well, how do you isolate that? Well, if you have your alternator and you have that heavy battery post, and then you have another connector here with multiple wires, depends on the design, it's easy to disable an alternator. Don't touch the heavy battery post wire, that one's hot all the time. All you need to do is shut the vehicle off, and disconnect the small gauge one, and then go take it for a ride, which eliminates the alternator from the equation, and see if your problem's gone. This is as simple as it gets if you think about it. Now, the key though would be, can you get to the connector? Right? But if you suspect an alternator is giving your vehicle a problem, that's what you can do. Disable it, run the car off the battery for your quick test drive and see how it runs. Ran beautiful with the alternator unplugged. So this was a picture of the AC voltage coming out of that alternator. You see I got like 2-volt peaks on this. So let me show you another one that might emphasize this a little bit better. And I've done this before in a different environment. I've done this. In fact, if you guys are following the recordings, I actually have this one in here. Let me go back to the beginning and talk about this. So I've done this kind of PowerPoint before. It's in my recordings. I think maybe section 1 part 5 or whatever is the last time I did this. So it's going to be on here twice, I guess, is what I'm telling you. All right, so I decided when I did this case study or this PowerPoint that I had a vehicle with a bad alternator, and I really struggled over the years interpreting some of these waveforms and knowing what was good and what was bad. And I decided to take a whole bunch of known good ones to go with this known bad one, so I had a real good idea of how to test these. So that's really what we're doing here. And one of the keys I will tell you guys is make sure when you're doing this that when we're connecting our voltmeter to the system, don't use the battery, use the back of the alternator, and I'll show you why here as we go. So when you're doing an AC ripple test, if you want to call it a ripple, and if I'm not making myself clear, what an alternator does is it takes AC voltage, converts it to DC, and then we charge our system with that. Alternator diodes go bad and they'll leak AC voltage into the system. That's what we're talking about. So if I didn't say that already, that's what we're doing. So if we're checking AC voltage in a system, we set our voltmeter to an AC mode. We connect to the battery post. This is the heavy cable. We connect our voltmeter positive to the back of the BAT post on the alternator, and then we connect our ground of our AC voltmeter to battery ground. And that's where we want to take that measurement. I have found if you take that measurement at the battery, it will be cushioned and it won't be as pronounced as it is on the BAT post. So that's what I'm doing here on this 92 Buick. Why did I pick this car? Because I wanted some known good ones. Okay, so this is a average voltage scale. This again is a graphed. Can't see that. This is a graphed AC voltage signal. What are we reading? The spec I'm giving you is 0.3 or less, or another way to write that would be 300 millivolts or less. How's our AC voltage on this alternator? It's good. Some other things you may want to do is turn the headlights on, blower on, experiment with RPMs, and take a look at it. So that's good. This is the same car showing the AC sine wave. So you see the difference. This is the AC sine wave. So the actual waveform of that system, that's what it looks like. Guys, this is what it is in a graph. This is the picture we just looked at. All right, so as you're learning this, depending on what you're doing, you'll read material that says less than 300 millivolts. And you're looking at this waveform here. What are we seeing? Look at this spike here. I mean, the value of that's -1 is here, and +1 is here. So that's at least a 2-volt spike in that waveform. Wouldn't this pique your interest if you're first learning about this? Wouldn't this pique your interest and say, hey, there's a problem here with this diode, I may have a bad alternator, and if you're reaching for a cause of a particular symptom, you're going to grab onto this. Yes, sir.
Would that be like a short in the system? Like
Good.
a spark going off?
This here,
Yeah.
what we would say with this is that is a diode that is leaking. And without going too much into the operation of an alternator, what we're doing, and I really need to pull up a good picture, and it's been a while since I've done that, but what we're doing is we're taking a sine wave and we're clipping off the peaks and valleys of it, really creating a DC constant from it. So in short, let's just say this Dustin? Damn, why do I want to call you that? Brandon, sorry. I've called you that twice now, haven't I? I'm sorry. It's the beginning of week 2. Forgive me. It usually takes me about 2 weeks or so to learn your names. Brandon. What we would say with this, our suspicion is we have a leaking diode. So that diode is not taking that AC voltage and converting it to DC like it should be. Okay? By the way, as you can see, there is some acceptable amount of AC voltage allowed in a system. So maybe a little bit of insight might be needed here. Wish I had a better picture of this though. Where is this? Let's talk about where that is riding. If I were to look at a alternator pattern and have my scope set differently, what we would see is 14 volts, maybe 12, 10, and so on, and you would see a flat line 14 volts on your scope. I think we can all picture that. That's what we would see if we connect a voltmeter to the back of the alternator. We'd see 14 volts, and if we were looking at it on a scope, we'd see a 14 volt flat line. So where is this? What I'm doing with my scope is I'm pulling it out of here. Believe it or not, this, what we call ripple, is acceptable, and it is where? It's up here. It's just not able to be seen on the scale that maybe you would pick if you picked this up here. So what I've done with my scope is when you set a scope to AC, what's called AC coupling, we block all of the DC constant and we just look at the AC ripple. If you look at my settings, this is 3.5 volts up here. This is -1. This looks like maybe about a 5 volt, maybe a 5 volt setting. And you see how we're hovering around 0? I'm gonna have to show you this later, but that's what we're doing. We're taking that 14 volt flat line, we're filtering it, we're blocking the DC, and then we're zooming in on that waveform. Okay, in this picture, you see the green trace? The green trace is measured where? I have it listed here. It's measured at the battery. So do you see why we want to measure at the alternator? Which one gives us a better picture of what's going on in that system? The alternator post. Questions so far? Hope I didn't lose you with the scope setup. AC-DC coupling might not be the right time to talk about that. We'll do that a little bit more later. I can expand on that for a second if you want, if there's any questions on that. But take this note. DC, a scope set to DC will show a scope set to DC volts will show both AC and DC voltage. I get that a lot. Is how to see an AC sine wave, do I need to set my scope to AC? The answer is no. A scope set to a DC voltage scale, also known as DC coupling, is another term that you'll see. DC coupling, or if I DC couple a scope, maybe couple would be better. That's how my Pico is worded. If I DC couple a scope, DC volts will show both AC and DC voltage. A scope set to AC, or also known as AC couple, if I AC couple my scope, it blocks all DC voltage. Does that make sense? It's a way that I can zoom in on a diode pattern on an alternator. Okay? We need to know how to do this for other stuff too. Any changing voltage will be seen on an AC coupled scope, but any steady voltage will be blocked. And over here, graph, that's a graphed version of this, the same yellow trace here. But guys, this is a good alternator. Brandon, the spike here, I'll just say this right now, is normal. So let's keep going. I'll show you the bad one here in a minute, what we look for. Let's go to another one. Same car, zoomed out. So this is zoomed in on this yellow trace. This is zoomed out, and again showing battery and alternator. Look at these spikes. You know, we might be looking at this too. There's negative 0.5, there's positive 0.5. We might say to ourselves, wow, that's pretty bad. Guys, there's nothing wrong with this alternator. You can see maybe now why this has been a struggle for me over the years looking at these. That looks like maybe that alternator is going bad. Look at all these spikes in this picture. Let's keep going. This is a 99 Subaru, just a student's car. I think these were all my students' cars at the time we did this. This is our graphed signal. This is our graphed AC signal. How's that number? That's good. So the number I'm giving you guys, that less than 300 millivolts, that would be a graphed or average number. So if you would connect your multimeter in an AC scale to the back of the alternator, you can rely on that number. Okay? That's not scope numbers. Let's see what this one looks like on the scope. There's some more of those humps and there's some more of those spikes. And again, to get this scope to read down here, this is set. I AC coupled my scope to make it read that. That allows me to take let's say my scaling here, I'm set 0 to 20, and time's not really all that important. This looks like, whatever. This is a 50 millisecond screen. If I look at the alternator, I'm going to see a flat line, maybe around 14 volts. I want to see the ripple that is in this picture. What do I need to do? I need to kind of zoom in on that 14 volts. And some ways I can do that, if I'm set on a 20 volt setting, is if I drop down to 10 or 5 or 2, I believe that's the setting on this particular scope. I want to maybe pick a 2 volt scale. The problem is when I pick that 2 volt scale, I'm really only now looking at about this much of the screen. And where is my voltage level? It's way off the scale. Does that make sense? It's up at 14 volts. So to zoom in on this, I set my scope to say 2 volts, but then I'll select AC couple, which does what to this 14 volt flat line? What's it do? It blocks the DC and then brings my line down here, and then I can really look at that pattern. That's how I got that picture. This is how you do it on any scope. I'm zooming in on that, although my Pico is one that I can take in the DC mode and I can put a zoom box right around that and I can actually zoom in on it without having to do that. So that's pretty cool. But this is a good one. Again, this is battery here, and this is alternator here. Zoomed out. This one looks a little bit better than the last one. No problem with either one of these. Let's keep going. 2000 Subaru, graphed frequency, or graphed AC sine wave, sorry, not frequency. That's a good number. There's 0.2, 0.4, this would be 200. This is 400 millivolts. Less than 300 millivolts, I like that. Look at these spikes though. Don't like that. This is the actual sine wave. And then they're zoomed out. So the spec I gave you is 300 millivolts, right? Would you maybe look at that and say, we have an alternator problem? That's 500 millivolts there at the peak. It's not a problem. There's a Mazda, an average. That looks good. There's that same Mazda on the AC coupled setting on the scope. Look at those spikes in there. I don't know why I didn't do a zoomed out version of that one, but look at the height. There's -5, +5. Up to here, look at this one. That's way up there. That looks like a problem, right? It's not. Here's what I've learned, ignore those spikes. Now here's a caravan. This is the one with the alternator problem. By the way, guys, we don't need a fancy scope to do this. We can do this with our regular voltmeter set in an AC mode. What would we see on this caravan with a regular voltmeter set in an AC mode? What's this number? There's 0.4. This is 400 millivolts. 0.6 is 600 millivolts. And somewhere around 500 some millivolts, I'd say this line is. What's the number I gave you? Less than 300. So you guys see right away, we would see this problem with a regular multimeter. But where do we want to be connected? We want to be connected at the BAT post to the alternator, not the battery. And I showed you why. You can see if we back up a couple of images, you see how clean it looks, right? Look how clean that looks. This same pattern when we're at the battery. And that's AC coupled. That's not an average anymore. Oh, this is scope. Scope settings. Don't go to the battery. Go to the battery post of the alternator. Okay? Symptoms of this van. I'll save that for a minute. Here's the pattern of the same thing we've been looking at. We AC couple. Now I got my colors backwards for some reason on this capture. The green trace is the BAT post of the alternator, and the yellow trace is the battery. So we're kind of flip-flop from my other pictures. But you see those spikes. Those spikes look horrible, right? It's not the spikes where your eyes should be looking. It actually should be really what the battery is showing. Here's where your problem is. This is your problem. I want you guys to look at this for a second. We'll go back and look at the other ones. It's not the spikes that are the problem. It's the entire waveform that's hovering up and down. Look at the other ones. They're not doing that. Here's where our eye is on these ones. See, we're kind of ignoring the spike. Do you see the difference? Do you see where we're hovering around for this one? Looks pretty good, right? Let's go back to another one. Where's our eyes focused? Here. Right here. How's this pattern look? Good? Let's go back. This is zoomed out, same one. Where are we looking? Right here. How's this one? Good? This one. Just drawing in green. That one's good too. And again, all right, so let's go back and look at our alternator with a bad diode. See the difference? Huge oscillating spikes in that. In fact, this one was so bad we could see it at the battery though. Though if we measured this at the battery with our voltmeter, here's minus 500 millivolts, here's positive. You see, we might be around 300 millivolt average maybe. If we measured at the battery, did we potentially miss it? If we went to the battery, the answer is yes. Give me 1 second. Okay, so I know what you're thinking at this point, and that is, well, how did you know to go here? Here's the symptoms of this vehicle. It was at a transmission shop. No, it wasn't. It was at a shop that thought this had a transmission problem. The issue with the vehicle is it had a vehicle speed sensor code in memory. And what the transmission was doing, how many of you guys had transmission class? Anybody have? A couple of you had transmissions. What you learn with transmissions is the vehicle speed sensor is an input that's driven off of the output shaft of the transmission. So a vehicle speed sensor signal would never be occurring if the wheels are stationary, not moving, because the output shaft of the tranny's not turning. So should we have a vehicle speed signal in park when we're not driving the vehicle? No, never. So the issue was this van would go into a second gear lockout. Second gear, what they call limp home mode on an electronic shift transmission, would be one that you have park, you have reverse, and you have drive, but it does not upshift. It pulls out in second gear. It doesn't upshift, doesn't downshift. Would be a second gear lockout or second gear limp mode. This is what's wrong with the car. It has a vehicle speed sensor code in memory, VSS, and it is a hard fault. What's a hard fault mean? It's happening right now. He clears the fault code, comes back immediately. He's already changed the speed sensor, the vehicle speed sensor, and he's already replaced the engine computer. And he has disconnected the speed sensor and run new wires to the engine computer. So this is my VSS, this is my PCM. He's ran new wires. And guess what? Still has a vehicle speed sensor code. So this is where I get the car. I decided to actually I'll walk through this whole thing. I started. Do I have the? Yes. I started at the vehicle speed sensor. In this particular system, it is a 2-wire sensor. This is significant. Why did this affect the vehicle speed sensor circuit the way it did? Is the vehicle speed sensor on this particular car makes an AC sine wave. It makes its own voltage. Guys, this yellow trace is the vehicle speed sensor signal in park. The output shaft of the transmission is not spinning. You guys understand why it's setting a fault code. The computer knows we're not moving. How does it know we're not moving? We're in park. We shouldn't be moving when we're in park. These are switch inputs, which we'll be going into later. It's a switch input. Computer's looking, hey, we're in park. It also can use wheel speeds from the ABS system and look at those too. We're not moving. This shouldn't be here. Immediate fault code for the vehicle speed sensor. Would you guys, if it wasn't for this discussion, would you guys know what to do next when you have a good vehicle speed sensor signal, or you have a vehicle speed sensor signal that's occurring that shouldn't be? I mean, you know where we're going with this. Check out the alternator diode pattern at the bottom. Wow, it sure matches that, doesn't it? I mean, the frequency of these now, they're inverted from each other. Just mainly how I have my leads connected. They are, the frequency of these two are identical. Is there a little bit of a delay? It looks like it. You guys understand that this was a bad alternator? What did it get? Vehicle speed sensor, and an engine computer, and wiring, and I'm sure some sleepless nights. Don't you think? This would be one that would really beat you up. Why are we talking about this? It's another variable you guys need to consider when you have some weird things going on with vehicles. Okay? Any questions? You guys understand that this is a measurement at the back of the alternator is where we want to go, and that the spikes in these waveforms, I am not concerned about the spikes. What am I concerned about? The average that's underneath of those. What causes those spikes? I really wish I had a better answer for you. I don't. It's part of the diode operation and how it takes that sine wave and cuts it off. I don't know if they're using capacitors on some systems to make those spikes a little bit cleaner, but it's just part of the diode operation. You see more spikes in some than you do in others. We don't overanalyze those. We look at the overall average. In fact, I'm thinking, you know, after doing this now for years and seeing these problems, the average reading is really the one that'll keep you from getting in trouble, because the average reading kind of takes those spikes out of the equation. So does everyone understand the text here? The AC ripple test, the diode test. Where are we connecting our meter? Connect voltmeter to alternator, battery post, and a known good ground set on an AC scale. Maximum allowable is 300 millivolts. And I'll tell you what, if you get higher than 0.1 or 0.2, you might be a little bit concerned too. Major drivability problems. Which ones does it affect first? Any sensor that produces an AC sine wave, of course, would be affected more so by this AC voltage. I have a case study on this. There should be maybe in the future a hyperlink added here to see a case study on YouTube. It was on a Chrysler, and what's the SUV that Chrysler has? It's not a minivan, smaller than a minivan. Is it Pacifica?
Yeah.
Yeah.
You know what? Let me get the title of that pulled up. Hang on one second. Okay, this was a 2006 Chrysler Pacifica, but that doesn't matter. Here's the title of it: Alternator Diode Testing. So the note here would be this YouTube case study. This is Alternator Diode Testing. And just like the one I just described to you, this vehicle, you see on the image here, was reading 20 mile per hour in park. As soon as I started the car, leave the sound down for a second, I'll let you guys see that real quick. Actually, I think I started it was in park, and then as soon as I put it in gear, right? Now, maybe a question here would be why are we only seeing this in gear? It really has to do with computer inputs, and this same signal was here all the time, but you have to understand that sometimes inputs will override a particular output. For example, the instrument cluster on this is computer controlled, and it talks to the engine computer. They talk to each other, and when that instrument cluster computer knows we're in park, it pretty much is shutting off that output of the speedometer. Does that make sense?
Yeah.
That signal's still there in park, but why wasn't it affecting it in park? It had to do with that. You see where I'm connected is the battery post of the alternator, and I'm just using a voltmeter. Really, this is the Vantage Pro. This is a fast voltmeter, and it's a scope. And right now I'm on a scope setting of what? This is DC. So look at this line. Look at this line right here. When you see a straight line and dashes underneath, that equals what? This is DC volts. Okay? Scope set to DC volts, and I'm on a 20 volt. So this line is 1445. If you were using a regular multimeter right now, that's what you'd see. We're actually seeing the ripple problem already. Even on this scale, that's how bad it is. Can you see the ripple in that screen? You normally would not see that. And I'm on a 5-second screen. That's time base here. This one's pretty bad. This is the exact same problem I just described to you. How did I know right away that this is where I was going? I've been here before. And that's when I grabbed the camera. I'm like, hold on. It was like 20 to 2. And this was a friend's car, one of our students' friend's cars. He's waiting. I'm like, you just wait right there. I want this one on film. So this just reviews everything that I just did with you guys in the video. You'll see in the next step, I'm going to change this to an AC coupling. So it's 20 volts. I'm describing that. Then I went to, here's what I'm doing now. I changed the time base. See, I went to 50 milliseconds and 20. And then now what I'm looking at is the same picture. Where were we a second ago? What was my time base setting?
5.
I was at 5 seconds, and what we're doing is we're adjusting time here. I'm now at 20, and now we see that ripple in there. This one's bad enough to see it on a 20 volt DC scale. That's pretty cool. We see a ripple problem. Come on. Unclear. Thank you. And then the next step, watch, I'm going to change my voltage scale because I want to zoom in on that. So where's my signal at? I changed it to 10. Where's the signal?
14.
It's still 14. I'm off the screen, right? You guys follow?
Yes.
See the arrows that are telling me, hey, out of limit here, you're off the screen. By the way, there's no such thing, guys, on a voltage setting of out of limit. You're not on the right scale, period. There's no such thing as what we're seeing here, which is out of limit. It is out of limit, but it's out of limit for the scale you picked. So I don't ever want to hear I have an OL on voltage. You say OL on voltage, you're on the wrong scale. Not the same thing with an ohm meter. So then I drop it down. Really, I want to look at it on a 2 volt, and I can't. We're way off the screen. So now what I'm going to do is AC couple. So you can watch how to AC couple a see what I did? You see the AC coupling? So I'm going to take this tool and I'm going to tell the tool, hey, block all the DC, just show me the AC. That's how I'm doing it. Selecting channel 1, I'm going to AC couple it. And you'll see on the box that we just talked about with the straight line and the dots, just to the right of number 1 that's blue, you're going to see, oh, I thought I was incorrect. I thought that was going to change to some other symbol. It's not. I'm just AC coupling a DC setting. You see how I'm hovering around 0 now and I was up at 14? This is how you do it. Questions? Everybody comfortable with what we're looking at? It's a lot more pronounced now, isn't it?
Yeah, it is.
You see the settings I had to go through? This is all just learning how to use your scope, what I'm doing here. And again, we're not worried about those spikes, are we? What are we worried about? The entire oscillation on that picture is what we're worried about with an alternator ripple problem. And then what I'm showing, nice thing about this is where I'm pointing, that's a min-max. So that's -2 and +2. And then I'm resetting that to make sure I'm catching it right. Yeah, 2 volt peak to peak, almost 3 volt peak to peak. Huge number. And then later in the video, I describe, is that one at the battery? Hang on. Is that the battery?
The output speed of that sensor, there's no signal there at all until the wheels start turning.
Okay, so the trace underneath it is my output speed sensor, my vehicle speed sensor. Same exact thing. Why is the speedometer reading 20 miles per hour when the car's not moving? Bad alternator. Cool? Just another thing you want to put in the back of your mind. All right, so that takes care of section 1. Your test will be tomorrow. There is one other one that I have in here, but I'm not doing this one with you. You guys can watch it. I already have this one recorded. It's not all that important. It's a functional test of a converter. I'm not doing that one with you right now because I don't do these 2 tests ever anymore. This is before OBD2, and the last time I did a HC test or a CO test of a cat like this would be pre-OBD2 cars that were not passing emissions, and I wanted to check the converter function. Now we have OBD2 that does catalyst monitoring, and I think we'll save the cat monitoring tests for section 4 and 5 when we do oxygen sensors, and I'll show you how it's being done now, and we'll skip that for right now. But that's the rest of our section 1 material. Our test will be tomorrow on this. Why don't you guys go ahead and take a break.